let's begin. So today I'm going to tell you about something new. I've been telling you, I've been going to be telling you for a while. So I'm going to tell you about distributions over matrices, but not just any matrix, positive definite matrices. So just as a prelude, we're going to be putting these over things like covariance structures or inverses of covariance structures. And so that's going to be the name of the game. Where do we see, why do we need to do that? Because if we see high dimensional data that's correlated, we need to learn what that correlation structure is. I will remind you that sometimes the variance is the most important thing in the whole system. So when I say variance, I mean covariances and all of that stuff. So a lot of people use just that mechanism to model. And so there's a lot of research that goes on in how to do this in high dimensional spaces, and if you have maybe block patterns of things. Maybe you already know what you're looking for block zeros. I'm going to talk about this rather generally, but where we're going is covariance structures, all of this. So without any further ado, here's what a Wishart looks like. And so V right here is our random variable. So this is going to be a k by k positive definite matrix. Okay, so what does positive definiteness mean? Greater than 0. So I believe the actual distribution is on non-negative matrices. So that means that an eigenvalue can be 0, but let's just call it positive definiteness right now. And so, but I do believe that the actual condition is non-negative. So just no negative eigenvalues in the system. But we'll call it positive stuff. I always get worried if you don't have that. But technically speaking, you can. Okay, so that's one definition of positive definiteness. It works for me. So every submatrix is positive definite of a positive definite matrix, so on and so forth. So all of those definitions that we've had before. So what does it mean in terms of the geometry of a system? Like what everything would look like? It means that it's convex. So it's like a parabola or something like that. I don't have weird inflections. So maybe you've never seen the geometric interpretation of eigenspaces, but that's what it might mean to you if you're a geometry. So there's going to be a couple parameters in our distribution. So this one right here is kind of like a scaling parameter right here. So this is, or sorry, not a scaling, but a shift parameter. It actually wraps up both of them, but this is going to be a k by k positive definite matrix, and this is going to be a scalar right here. So here's our density function. It's just this. Boom, we see the random variables show up in two different places. And so notice first that if V was a variance, not a matrix of variances, that this would look like a gamma to you. So this looks very gamma-esque to us. We have this thing going on right here. So I have my input matrix inverted. And so since it's positive definite, I've got all these positive eigenvalues. It's a symmetric square. I can invert that thing. Okay. So we always need to check, make sure that we can invert everything, but it shows up as an inverse right here. And here's our random variable again. Somebody please tell me what the trace is. So this is just a matrix right here. This is going to be a k by k. And then we're doing some operation on it. There's a lot of different definitions of a trace as well. They're all equivalent to each other. What's that?
The sum of diagonals.
I like that one. That's the easiest one to do proofs with. So let's just say sum of diagonals. Anybody else got something? Let's say, I could teach that to a second grader, so that doesn't sound very good. So Dan, spice this up. Some of the eigenvalues. So now I need to go to college to understand what this thing is. And so some of the eigenvalues as well is what it is. So, or equivalently, some of the eigenvalues. somebody asked me to compute the trace of a matrix, I'd probably just sum down the diagonal. I probably wouldn't go work out its whole eigenspace, all the associated eigenvalues, and then sum them up. That'd probably be the wrong way to do it, but these are equivalent. Okay, so let's write down a few facts about this. The expectation of V, and this is going to be conditional on the parameters that govern the distribution. This is going to look like this, gamma times omega. So when I said that matrix right there, omega, kind of centers the whole distribution, and then I said it scales it as well. It's kind of wrapping up both the scale and the centering of this. Very common thing to do if I wanted to interpret omega is where this distribution is centered. So it's centered around the whole matrix. We're getting random matrices around it. You know, they kind of look like omega. How much do they look like omega? Well, it depends on how big or small that number is, right there. And so if you wanted to divide this whole thing out, some people will do this. I could easily put in divide by gamma right here. I could divide this by gamma as well. So take the inverse on the outside of it. I'm going to erase that in a second. I can divide by gamma here, but I've got proportionality and gamma is fixed, so I'll refrain from doing that. Sorry, it would have been right here. I'm going to refrain from doing that, and then our expectation would be that. So if I just take that centering matrix and I divide it by the same gamma number that I'm using to scale everything, then I can interpret omega as the centering matrix. I'll show you that again later. Let's just get rid of this. This is just how we interpret these parameters in here. And gamma has something to do with the variability of the system. How diffused I am around these matrices right here. So variability of Vij, so each element, we can only write these down as elements. I don't have any fancy notation or linear algebra to explain to you what they all are. I believe it's this. Vij squared plus Vii times Vjj. So that's the variance. So you can see that as gamma is getting bigger, we get more and more variance in the whole system. Of course, if I divided everything by gamma, that would be on an inverse scale. Okay, so this is kind of the interpretation. So I'm centering everything around these matrices right here, which is just a scaling of omega, and gamma is controlling the variance, how I'm bouncing around that matrix. So stochastic distribution on matrices. So Bayesians always want to do this stuff, where we don't really care how complicated the substructure is that you're looking at. We're going to put a probability distribution on it. That's the name of the game every single time. Okay, so all of these operations are pretty easy to take. Just note also, this is a determinant right here. What's one way of phrasing the determinant with respect to the eigenvalues? Dan, help us out with the other operation. Multiplication, so product of all of your eigenvalues. Okay. So here's the question. Well, actually, let me write down an example. Consider this example. I'm going to say X is multivariate normal. I'm going to say that it's centered around some vector right here. So let's say this is a k by 1. So it's just a k vector. This is going to be a k by 1. And there's going to be some covariance structure. So I'll just write this down as covariance. Let me write down what the PDF looks like for you. So Px given mu sigma is going to be proportional to sigma determinant inverse divided by half e to the minus 1/2 x minus mu transpose sigma inverse x minus mu. And I just haven't put in my 2 pi's. So you'll notice that in every calculation we've ever done, we've thrown away our 2 pi's, so I'm not even going to write them down. How many are there? There's root 2 pi raised to the k. K of them getting producted in. Okay, so I've got a question. What's the conjugate prior for sigma? Now, obviously, I'm setting you up. So you'd want to go over and stare at this thing for a little while and see if I could multiply that into that thing and recover the same form. So that's what conjugacy is all about. Once I slide it through the likelihood, I multiply their densities together, I get the exact same form. So when I use something as a prior, I have the same form as the posterior. Just updating the hyperparameters. You can see in computational code, or in the 1960s, or whenever, why that's an elegant thing to do. You don't have to change the distribution every time I get a new data point or something like that. Just change the hyperparameters. What do you think the answer is? Doesn't quite look the same, does it? It's this thing over here. There's a bunch of operations taking place. Does anybody just know the answer and want to be obnoxious and shout it out? Sierra?
Conjugate prior for sigma, Wishart. No, inverse Wishart.
Good.
Yeah,
so
my bad.
Sierra just did a couple of calculations in her head, and it turns out it's inverse Wishart. So that's kind of obnoxious because I just showed you what the Wishart distribution is. And so what's the inverse Wishart distribution? Well, when I invert V, so V inverse, what's the distribution of that? And you'd have to work through everything. Again, I don't really like to think about the inverse distributions and everything else, so I always do everything on the inverse scale. This one's kind of funky, that inverse Wishart is the distribution that models our covariances, and Wisharts are going to be the thing that are conjugate for our inverse covariances, and that has a name, and I'll introduce it to you in a second. Keep in mind that's exactly opposite for the gamma. So on the variances, you know, if we were going to do something, so we put things on the precision scale so we could model them as gamma. If we did it on the variance scale, it would have been inverse gamma. This is exactly opposite of that. It took me like 2 years to remember that. You know, I always make this mistake. And so when I ask you to do a problem on this right here, you'll have to run off to an inverse Wishart table and understand what this whole thing is. I haven't written down normalizing constant, all of it. It's a p-dimensional gamma is what you end up getting. And so basically it's a whole bunch of little gamma functions. I did write down this part of the normalizing constant just because when you do some of the problems and I ask you to integrate over something and recognize its distribution, usually you're taking the inverse of the normalizing constant and working through it. This part you would need to know in the problems I asked you. The little gamma function part doesn't matter. Let me just ask one more question before we walk through the details of this and show that Wishart is the conjugate prior for the inverse of this. If I integrated through this, this is a matrix. What do I mean by integrating? So if I integrate over any density, P, V, given gamma omega, and then I end up integrating with respect to V right here, we know that this thing is going to be 1, if that's a density function. And it is, if you normalize it all properly, so you'd have to put in all the gamma terms. What does this mean? What does it mean to integrate over a matrix? What does it mean to integrate over a vector? I've been dealing with vectors a lot. Never really had any problems with that. when I asked you to play around with multivariate normals, maybe you thought about integrating over mu, probably did it without even thinking twice about it. What does it mean to integrate over a vector or a matrix or higher dimensional analogs of that? Just say it. Okay, so I'm not there. Any math majors? Melissa? Oh shoot, I don't even know what that means. Been thinking about topology for way too long.
Should be a inverse of taking derivative of a vector.
Yeah, so what does that mean? So when I take a derivative over a matrix, what does it mean? So you're right, obviously if they're inverse operations, I do the same thing. What does it mean when I take a derivative over a vector? For each, right? So I just take the derivative, all the partial derivatives all the way down. So I just do all the partial derivatives. Yeah, so this is just a multiple integral over all the elements. Since it's going to be symmetric, I don't need to integrate over all of the off-diagonal. I only have to do one set of them. That would be integrating over all of them. And so what does this mean? It means to integrate element by element. So just so you know, now that would be an onerous task to go through and actually do it. And so if you were to integrate all these things, and so what I would recommend is when you try to work through these integrals, you run off to a table and you see what somebody else has already worked out for you. And so I think this distribution came about in 1928. So poor John Wishart had to go through and probably, integrate through all this stuff, understand it, and now he's written it down for us, and all we have to do is understand what the properties of this distribution are. And so again, all these derivatives and stuff like that, and integrations, there might be fancy, elegant solutions to that, but it is just an element by element calculation. Okay. So I think I want to keep my Wishart around so we can stare at it. Just keep this big on the board. Just a couple notes. Homework on Wednesday. Review Wednesday 6:30. We'll do yes, no, maybes. That means you can come in and say, is it on the exam? If you want to ask anything else as well, that's always open. So a useful review session for preparing for the exam, which is going to be next Monday. And I don't think there's any ambiguity when it's already this Monday, what next Monday means. I think this is the only time that's not ambiguous. I think. And I'll remember this. Expectation of B given gamma omega is equal to gamma omega. I always tell you to remember what the expectations are because it helps you to guide your thinking. Is this a reasonable answer? In expectation, humans are pretty equipped to think about expectations, it seems, but nothing else. I might be projecting. Okay. So we've got a normal. Let's just go through. We've got n data points from a normal. So let's go back to our example and say xi's are going to be multivariate normal with mean mu and covariance sigma squared. I'm going to say this is known. Okay, so it felt very much in the beginning of the class when I say, I'm going to assume this thing is known, it seemed like a calculation we'd never use. And now I've given you a trick where you use it all the time. So what is that little computational thing that we do where we fix all the other parameters? We call them full conditionals.
Q sample.
give sampler. And so this is going to immediately set you up for plugging this thing into a give sampler. Beautiful thing. We'll say we've got n data points. Of course, I don't need all n data points to figure out what the conjugate prior is. I can just use the functional form of what it looks like under one data point, but it's probably good to just work through the whole posterior at the same time. So I think we'll do this all at once. So these are all II. What I mean by that is the elements inside of X are definitely not independent, but each one of these vector realizations is conditionally independent of each other, given that I know the other parameters. Okay, so that's the lingo. And so if we want to work out what are, oh, and I should probably write down the answer is Wishart is conjugate for sigma inverse. This is the one that I always use. I always model the precision. So let's give that a name. It's called the precision matrix. I actually like staring at this thing a lot more than I like staring at covariances too. I'll tell you why in a second. So, and inverse Wishart is conjugate for the covariances, sigma. Okay, so Sierra told us this one, so I inferred real quickly the other thing. We'll see what Sierra was doing in her head when she was dicing this whole likelihood function up to make it look like this. What do you guys know about the precision matrix? Let me just show you an example real quickly. This is just a side. We'll come back to this example in a second. But consider this. Consider some model that looks like this. I'll say xi is equal to theta such that theta is, the norm on theta is less than 1. So this is just absolute value right here. So I have a stationary model. We've discussed this very briefly. And let's say this is just normal 0 sigma squared. So here's a question. What does sigma look like? For this process. And some of you could probably work out all of the entries in that covariance matrix. So we can see that all of the xi's have some correlation in them. Okay. I'm writing it down as a process, but these are all normally distributed, these little things. And so the x's are centered around somewhere where the x is centered their previous value. Maybe in some stationary model they tend to something, but let's write down the full conditional model. But these x's are also correlated with each other. And so there's a big covariance matrix. And so I choose to write it down like that. I'll give you a hint real quickly. I need xi minus 1 to update xi. And so they're very correlated with each other, and it has something to do with this parameter. And you can work out what it is. If I asked you how much correlation there was between x2 and x0, you might say, well, they're correlated with each other, but they're conditionally independent. Okay, so given that I know the previous draw x1, then there's no information there. But if I take that away from you, to generate x1, I needed x0. To generate x2, I needed x1. And so x2 is correlated with x1. And it turns out the answer to this question, at least to the description that I'm looking for, is this thing is dense. It's dense. I.e., it's a square. If I do this n times, then I have this n by n matrix that I'm building up, and it's dense. Every entry has something in it. Here's the amazing thing. So, question, for the exact same thing, what does sigma inverse, the precision for star look like? So if I form this covariance matrix and I inverted it, anybody have any idea? I'm going to give you a handout on this. So I wrote up a 2-pager on the interpretation of elements in here, but it turns out this is a tridiagonal. And this is very cool. It ends up looking like this, tridiagonal. And it has a meaning to us. It says that everything is conditionally independent in this particular way. So if I want to infer what this little variable is, all I have to do is look over to its neighbors. They're the only ones that have information. Everything else is conditionally independent. So given its immediate neighbor, everything else is conditionally independent. So elements in the precision matrix tell us about conditional independencies. That's very cool. And so if this was an AR2 process, I would pick up 2 more bands on this process. And so the precision matrix, to me, tells us what's conditionally independent of everything else. And so there's a whole field that leverages this, Gaussian graphical models, and their whole game is to figure out who's conditionally independent of who else, what lives in a block, and sorting through everything and figuring out what these block zeros look like in the conditional independent structures. People that work on Wall Street do this. They try to figure out which markets move together so that they can hedge. So I've got a lot of friends that make $1 million every year just off of that idea, and basically they're staring at complicated model-induced precision matrices. They're looking for zeros so that they can figure out what markets are doing with respect to each other. Okay, so precision matrices are cool. I'll have a handout you can read through. If you've ever taken a regression 101 class, these are partial correlations. That's what they are in the precision matrix. They probably never told you that. They didn't tell me in my class. I didn't learn that until graduate school. But I had already learned about them, but I didn't understand them in terms of matrices. Okay, so this gives us a lot of opportunities to induce priors on things. You might say, I'm going to put a prior on the covariance on the precision matrix, and I'm going to look for things that start to deviate away from 0. So I might say I want strong shrinkage towards 0. If it's around 0, I want to push it towards 0. But if it's not 0, that means something. Because my data is overwhelming, what I think a priori. And so a lot of people go about business that way. When I tell you about point mass priors, basically I can put mass at 0 and then say maybe it's something else in the continuum, but I want sharp mass at 0. A lot of people do that in Gaussian graphical modeling. And so I'll bring this up again and tell you how people extend point mass priors to these sort of models. So a lot that we can do once we understand the structure better. Okay, let's just do the easy stuff. The likelihood function. So the likelihood on sigma inverse, given everything else, I'll write down cap x is just my array of vectors. x1 to xn. Likelihoods are always written down up to proportionality. And this is going to look like this. Sigma. Oh, and I should probably say this is a k by 1, just to remind us. So we'll use the same dimensionality. And so I'm going to write down product, because everything is conditionally independent. Sigma minus 1/2 e to the minus 1/2 xi minus mu transpose sigma inverse xi minus mu. Please never divide by a matrix in my class. So Again, it's one of my pet peeves. I know no matter how many times I say that, somebody's going to do this. Okay, so let's just rewrite this. Sigma determinant minus n over 2. It's just a scalar, so it gets powered up. E to the minus, and I've got a little bit of unfortunate notation, so I'll try to be careful and write down my indices to show you that my sigmas mean different things. This one's an operator. I goes from 1 to n. xi minus mu. Sigma inverse, which is covariance. Be careful with these two symbols. Xi minus mu. So there's my likelihood function. And I go and I stare at this thing right here. I put in a sigma inverse for V, and I think they don't look anything the same. Kind of look a little bit the same. There's something leading out here, but you'll notice that if I ended up writing down a prior, on sigma inverse, this is what my prior is going to look like. This is the prior that I'm saying is conjugate. And it looks a little bit funny because I've got this minus sign out here, and I've got this minus sign right in here. So how about this? Why can I do that?
So that's property of the determinant.
It's a property of determinants. And so if you didn't know this, it's a good thing to know. I used to use this trick all the time when I was working through transformation of variables in higher dimensions, those sort of problems, that sometimes it was easy to take the derivatives in one space and then invert everything and plug in all the transformed variables. And so it can just make problems easy. But this is a property of determinants. So note, determinant property 1. Is simply that determinant of inverse is equal to inverse of the determinant. I'll just write it down like that. If you don't like me using dot, you can use anything you'd like. So that's always true. So starting to get a little bit better, I've also got this chunk right here, and I've got a trace right over here. So somehow I need to shove a trace in there. So I'm just going to do it. Trace. Why can I do that? I just did what I wanted to do in one line, but I haven't justified I can do it.
It says the precision matrix has zeros to juice out of those values.
That's one theory. So it turns out it's true and it does work out. So, but it would happen irregardless if that thing had zeros in it. So I haven't said that my precision matrix is coming from an AR process or something, so there might not be any zeros in it.
Trace of scalar is
What's that?
trace of scalar is just
Yeah. So trace of a scalar is a scalar. This thing is a scalar. What's the dimensionality of this thing? I can't just go and take a matrix and take a trace around it and say it's the same thing. I've changed the whole dimensionality of everything. But what Daniel just told us is this is a 1 by 1. And so this whole thing right here is a scalar. In the Wishart form, it's a matrix. So that's a little bit weird. But in this form, it's a scalar right here. And so that's a 1 by 1, but summing up the diagonals of 1 by 1 is just that 1 by 1. I haven't changed anything. And so here's another property of traces. As a note, say A, B, and C conform. So I can multiply them together. I don't really want to say what their dimensions are. So when I say conform, I just mean I can product these things together. So this dimension is that dimension, this dimension is that dimension. That's all I'm saying. This could be, you know, just some matrices. This is true. Trace BCA is equal to trace CAB. So not every permutation is allowed for, but the cyclic ones, you got it. So these are just cyclic permutations. And so I just took this thing, spiraled it over here, and then I took this one, I spiraled it over that way. I'm going to ask you to prove this on the homework. If you don't know how to prove it, go grab a linear algebra, and it's in every single one. And so when you first start playing around with traces, they'll have you do this calculation. There's another property as well, and I'll just tell you this one. So here's trace property 1. So on the current homework, there were these mysterious problems pertaining to Wisharts and all this stuff. You can already infer. I'm going to ask you to do one of those problems. So if you want to head start, go ahead and start running through them. It's pretty easy to show. There's another property. Let's just call this trace property 2. So trace of A plus the trace of B is equal to the trace of A plus B. Daniel, help me out. Why is this true? This one's so easy that Daniel is like, I don't want to say the wrong thing because it's too easy.
Yeah. Just because it's like, would you just think the diagonals, yeah, it's obviously true.
Yeah, because it's obviously true. So it sounds right. No, you said the right thing. So because of the so if I sum the diagonals, so if I add those two diagonals together and then I sum them down, it doesn't matter which way I add things in. And so I can either sum the diagonals and then sum them, or I can sum each diagonal and add them together. And so it doesn't matter which order I do those things in. So this one's obvious. I'll ask you to prove that too, but that's a one-line proof. And so we're going to use both those things. So we slotted in trace in all of this. What I'm going to do in this is I'm going to back the sum out. So what I can do is I can slide this summation operator over the trace right here, and then I can spin these elements around. And so I'm going to do both moves at once. So let's just do that. We've got our trace properties. We'll use them. And so my likelihood function, let's just write down where we're going. We're trying to get a posterior distribution given all of our data and mu. If you like to condition on your hyperparameters, go for it. It's fine. I just usually don't write them down, but I like everybody to always remember hyperparameters are involved in everything. So this is going to be proportional to my likelihood given mu and x times my prior. So I'll just write down P sigma inverse gamma omega. So I'm going to make a couple steps right here. I've already slid that -1 in there. This is going to be n over 2. It's going to be e to the minus 1/2 trace. And I'll just truncate everything and just write TR. This is going to look like this. Write it like this.
transpose.
Times my prior. And so I'll come back around to this in just 1 second. Times, I'll just write this down right now, times my prior. We'll finish it in a couple lines. So my likelihood, I've used 2 steps to rewrite it. What I did first is I slid this thing outside of the trace. Then I did a cyclic permutation, and I moved this over here. And so this used to be an inner product. And now, because I did this cyclic permutation, and you can check the dimensionalities and everything match up, this is now an outer product right here. So this is a matrix. So the transpose is over on the other side. So this notation's a little bit atrocious, but I think we understand it with the indices. And so what I did after I did the cyclic permutation is I dragged the sum right back in. So I used both of those trace properties. Now all I have to do is multiply by my prior, and we can see with it in this form that everything's going to turn out just right. So let's just finish the calculation. See if it makes sense. So let me get rid of this and just put down my prior. So this is going to be sigma inverse gamma minus k minus 1 over 2. E to the minus 1/2 trace omega inverse sigma inverse. Sigma inverse because my measure is on the precision. And so now I can combine everything. This combines trivially with that. Now I'm going to take my exponential terms, factor out the minus 1/2, and I'm going to add these 2 traces together, which is the trace of the sum of these 2 things. So this is sigma inverse n plus gamma minus k minus 1. You never want to absorb the k minus 1 in there. You're always going to be looking for it. E to the minus 1/2 trace sum. Oh, and I'm going to factorize out sigma. I can roll this thing around right here. It's going to sit on the exact same side where that sits on, and then I'm going to factorize it away from everything. So this will look like this. So one more cyclic permutation, drag this thing over here so that I can write everything like this. So this is going to be sum. I goes from 1 to n, xi minus mu, xi minus mu transpose plus omega inverse. I've got a trace down here. Sigma inverse. So only this stuff is in the sum right here, not adding that up any times. So basically just a couple applications of trace rules 1 and 2. And so what do we recognize this whole thing as? This is Wishart. What are the parameters? Gamma plus n. No surprise, n shows up over by that scaling factor. And then I've got this creature right here. Sum of outer products, xi minus mu, xi minus mu transpose plus omega inverse, and to be consistent in my notation, I need to invert all of that. Remember that when I wrote this down, this notation, I just had an omega sitting here, and it showed up as omega inverse when I wrote down the density. And so what's the expectation of this thing? So our expectation of our precision, given all of our data, and I'll remind you, we told you mu in all of this, so we're writing down full conditional posteriors, is this thing is going to be gamma plus n times sum, I goes from 1 to n, xi minus mu, xi minus mu, transpose plus omega inverse, all inverted. So that's our expectation. Does that make sense to you? Is that an intuitive answer? For me, I love it. So let's just remember, how would you estimate sigma if you were to estimate sigma? Sigma hat, you've gone to classical school, you've got a point estimator. What is it? If I told you mu, what would you do? So probably do something like this, maximum likelihood estimator, so we could do all of that. So MLE for sigma hat is going to look like this. Xi minus mu, xi minus mu, transpose divided by n. So that's what a lot of people would use as an estimator, right here. So this kind of has this form, but I'm regularizing. I'm regularizing there, and I'm regularizing here. So typical sort of Bayesian thing, that I'm averaging kind of my prior and my likelihood-based beliefs. So this is kind of a nice thing. People do this sort of anchoring all the time. They have covariance matrices, and they'll add something to it. So they might have some really heinous data, and they haven't gone through all of the effort to rip out all the multi-collinearities or anything like that. Maybe K is bigger than N. And so what will happen is this thing right here won't be full rank. So this won't be positive definite. We'll have 0 eigenvalues in there. And so this is kind of neat that if I add it to something that is positive definite, then I get positive definiteness back. You ever done anything like that? This is a typical regularization solution. And so add it to something and then work with it. So ridge regressions do things like that. It's a whole different sort of regularizing space, but they're very simple. You add it to something so that you get all the properties that you want. So don't push this thing too close to this. Like, don't make this right here have huge numbers relative to that. And so we can kind of see what the impact is and how it's influenced also by n. How much diffusion we put in through the prior and how it calibrates to n. In this case, it's additive. So I like this solution. You know, one thing that you could do is you could always take omega to be the identity. Or maybe scale it to that. If you say, I'm trying to look for conditional independencies, I want to maybe say, or I want to look for conditional dependencies. I might assume a priori they don't exist. And so the data has to tell me that they're there. And so then I would maybe take omega to be the identity, or some scale factor up to the identity. I think Sierra does that in some your research, right?
I stick mostly with variances because that's what our engineers like.
Yeah,
But
sure.
We can do precision.
It's
look at
still
it.
the same. So still the same thing. So okay, so she puts in I on the inverse Wishart scale because she can't tell an engineer what a precision is versus a variance. Is it true, JD?
Can't tell the difference.
Shouldn't meet our engineers. Anyway, let's come back around to this, and I'm going to motivate it with an example. So this is kind of a fun example that you're going to get to see. It's one of the first if sampling examples, where all of these layers come together. And so hopefully you've caught on to this real magic trick, this bazooka. If I can write down a whole bunch of conditional independencies, and I've got a for loop that I can run, I'm in business, and I can do full-blown joint influence. It's magical. So just write down your model, pick some good priors that maybe you can work with. It turns out the reference prior for this is an improper form of the Wishart model, which won't surprise you. And if you want to look at it, it's problem number 1 on the previous homework that I asked you not to do. And so that will have the all those reference properties that we talked about. Anyway, that's it for now. We'll come back to this and use it in a real example. See how we play with it.